we're continuing on with Class 7 in ES110. We're talking about some more vector actions going on here. We already mentioned the mixed triple product. Well, we mentioned one form of the mixed triple product where we took a lambda and dotted it against here. So now we could also have this mixed triple product here where we take all three vectors, right? So, but the first order of operation is to cross P and Q together, right here. So you cross P and Q, and then we get a new vector out of that, and we cross that's this guy, this blue one right here, and then we dot product him against S. And what we'll end up doing, this is a crazy way of trying to find a volume, right? So if you want a volume of like a prism, this oddly shaped prism, we can go ahead and get that with the mixed triple product. I don't know when that comes up very often, but maybe it does. Maybe just hasn't come up in my life very often. All right, so the moment of a force about a given axis. So that's a pretty good one, right? So that's actually kind of similar to what we just did in up here, right? I guess it's what we talked about right in there. Sure. And it's kind of what I did in this example right here, where I was no, not quite. No, what I was doing is just taking this vector and dotting it against here. But now what we're going to do is we're going to find the moment that's acting because of a particular force acting at a point, and then we're going to cross it against we're crossing it to find the moment, right? So we find a new moment, and then we dot that moment against a line, and this line, for some reason, we want to know what the moment is specifically about that line, not about the moment in space, but the moment about a particular line. And so these are all the lambda x, lambda y, lambda z's. We could put those right there in there, so we could do it in one step, as opposed to having to do it, find the moment and then do the dot product. We could stick it right here inside this determinant and take the determinant. And so the moment of MOL right here, that's the moment about O along L is what they're meaning. Measures the tendency of the force F to impart a rigid body rotation about this fixed axis. So we'll try to find an application where we see this. And right here, I guess we're just saying this about an arbitrary axis right in here. So this is sort of interesting right here. Yeah, this is actually repeating the same thing, I think. Sometimes we might want to do this particular thing, right? That we want to have it, that we have this point A right here, where the force is applied, and we have it. We have we want to find the moment that's caused by this, and then we want to see what's happening right here. So this is like an arbitrary one. This is the one that I thought that kind of like made a little bit more sense to me. If we wanted to find what this moment was going to do to try to twist the pipe and make the pipe make the pipe loose. So that was the one that I kind of preferred as an example. That's one reason why I picked it out right here. So let me do this and then maybe go home, because it's late at night. It's not late at night, but I'm the only one here. I must not have a life because I keep staying here after everybody else is. What is wrong with me? Okay, so in this problem right here, kaboom, we have a cube right here. Maybe they describe some motivation. This is sample problem 3.5. A cube of side A is acted upon by a force P along the diagonal of its face right here, right? So there's a force that's coming along right here, and we want to determine the moment that P makes about A. Right, that's a good idea, right? So there's going to be this force is acting onto this thing. We want to find out what the moment is about A, and then we want to find about edge AB, right? And then about a diagonal AG of the cube, and using the results of C, determine the particular distance. So now we want to find the distance between AG and FC, right? So there's going to be some line that we could draw in between there. Somehow we could figure out the perpendicular distance. So that seems to me like a whole bunch of crazy stuff to do without a whole lot of satisfying ending. Personally, I kind of like problems that have numbers as the answer, as opposed to just this random symbols. But let's go ahead and systematically go through here. We will find the position of first of F with respect to A right here, right? So we're gonna, because we want to get the moment of this force P about A. So the force is applied at F, so we need the position vector of F with respect to A. So we take a look at this thing and we see that we are, if we define, I think we need to define X as that direction. Let's say that this is Z, and let's say that that is Y right here. So to get over to here, we come over 1A. All right, and this thing has A on every side, right? So that's got lengths of A on all sides. So we come over positive A to get from here to here, and then we go down negative A. Right, so negative A, J, down. And then they're on the same Z, right? They're coming out of the board over here. So it's going to be 0, K. And then let's say that we also want to get C with respect to F. So now we're going to be able to define what the line is of that's acting on P. So we take C with respect to F right in there. And that's going to be on the same X plane right there. So it's going to be 0x. And it's going upwards A. And is it doing anything? Yeah, it's going in the negative A direction, right? In the Z, right? It's going backwards that way to get from here to there, right? So now we want to have the magnitude of this. Square root of A squared plus A squared negative A squared, I guess, huh? Right? So square root of 2A. Not hard to do. So when we get the lambda C with respect to F right here, all we do is take up, it's going to be 0I, and it's going to be 1 over the square root of 2 right here, right? J. Because we're going to take A and we're divided by this, so that's going to cancel out. And then we're also going to do the same thing over here, but it's negative, so it's going to be negative 1 over square root of 2. K. These are like 45 degrees. You got the idea, right? And so when we want to write out the vector P, it's going to be magnitude times that right there. Or 0I plus P over the square root of 2, J plus negative P over the square root of 2, K. And then when we go and we want to find this moment about A, which is the first thing that we got asked right here, we wanted to find the moment about A. We take the position vector F with respect to A, right? Because we're going to get to the spot where we're taking the force, so it's really going to be that line right there crossed with our P. And that is going to look like I, J, K, and then R, and we're going to go, this guy, A, negative A, 0, and then this guy is 0, P over square root of 2, negative P over the square root of 2. Close it up right in here. and we do all of this, let's take the cross product. So we're going to cross negative a times negative p over the square root of 2 minus 0, right? So that's that times that, I. Did I do that wrong? I think I did that wrong. No, I think that I did that right, but I wrote it down wrong on my sheet. I think I did that right. That times that, negative times negative, it's going to end up with a positive. Okay, we're good. So it'll wind up why I did this wrong. I won't remember that. Okay, and then minus, right, so now we're going to go this one and that one, so we're going to take this j, so we go a times this, so a times negative p over square root of 2, right, that one times that, and then minus 0, j, and then plus a, now we're going to take this k and we're going to go to this one, a times, so it's ap square root of 2, and then minus this one times that one, which is going to be 0, right? Okay, so what we're going to find for MA is going to be, we see that those are going to cancel out, so that's going to be a positive AP square root of 2 times I. There's a negative and a negative, so that's going to be AP square root of 2. And then look at this one's AP square root of 2. So we find we have the AP over the square root of 2 and times I plus J plus K. What does that tell us? I don't know. They told us to do it. The next thing they told us to do was to go about the edge AB, right? So the edge AB is entirely in the I direction. So what we would find, the lambda of AB, or B with respect to A, I should say, is going to be equal to just I right there. So if you take MA, let's see, I'm calling it MAG. Okay. I think I was going to call this AB. I don't know why I called it MAG right there. Yeah, it's MAB. Is simply going to be these dotted against each other. And I should write this B with respect to A right in there. So when we dot them, all we need to do is multiply all of the things by each other. And so all of them are 0 except for I. So all we really need to do is take I right here and multiply 1. Let's just say 1 right here, right? We don't need to, I don't know why I'm putting this 1. 1 is the magnitude right here. So we're taking all the and multiply by the magnitude of this one. 1 times the AP over the square root of 2, right? That's all that is right there. And done. It's A times P over the square root of 2 is going to be the answer to B. That was not very satisfying. Kind of boring, to tell the truth. And then the next thing we wanted to know was about the diagonal AG of the cube, right? So this AG is coming along right there. So what we really want to find is G with respect to A. Yeah, sure. So we get RG with this is supposed to be a G. It doesn't look like a G, does it? With respect to A is going to be, well, it's going to be A in the X direction. It's going to be negative A in the Y direction. And it's going to be negative A in the Z direction. Did I get that right? Yes, I did. And so what I find is AI plus negative AJ plus negative AK. And the magnitude of that, we can almost do this in our head, right? It's going to be the square root of 3 times A squared, right? A. So square root of 3A. It's going to be the magnitude right there. So the direction cosine of G with respect to A is going to be, we're just going to divide this by that. So we end up finding that we get 1 square root of 3I plus negative 1 square root of 3J plus negative 1 square root of 3K. So all we really need to do to be able to find the thing that we were looking for about the diagonal, we want to determine the moment of P about the diagonal, is take this moment right here, the moment that we had right here, and dot it against here. So we find M A G, right? And this is just going to be a value, MAG, right? And I wrote this one as a vector. Really, it's a scalar. I should have left it as a scalar. And I could leave this as a scalar. It's just a particular magnitude of the thing is going to be G with respect to A dotted against MA. And so what we're left with right here is, let's see, where are we? Right here. 1 over the square root of 3 times, and they're all actually all the same thing. So we go AP over the square root of 2, right? It's going to be plus negative 1 square root of 3 AP square root of 2 plus negative 1 over square root of 3 AP over the square root of 2. And so we're going to end up, so we have the square root of 3 and square root of 2. This is a negative 1, and so that's going to cancel one of those out. So it's really going to equal this, which is going to be a negative AP over the square root of 6 is going to be the answer. And I don't know, I have this kind of problem. I don't see the motivation to do it. I'd rather have like some story or something to tell me that I have to do it. And the last part of this, it says, using the result of part C, determine the perpendicular distance between AG and FC. Okay, so, I see. So what we're going to do is, like, if you have the force, right, if you know that what the force is, and you know what the moment is, you can find the distance that's perpendicular right there, because the definition of a moment, right, is if here's the force and it's going, and here's the thing that you're tuning about, there's the distance, right, and that thing is going to create that moment, right? This moment is defined equal to F times D, where they have to be perpendicular to each other, right? So if you want the perpendicular distance for something, take the moment and divide it by the force magnitude right here. So we have a magnitude and a magnitude right here. We happen to know that the moment of AG right there that we just got. So we know what this is. We know what this force is going to be. So we could find what that perpendicular distance is, even though it's hard to picture where that's going to be, right? We'd have to twist around and that kind of thing. So what we end up finding is that moment of AG is simply just going to be P right there. So the distance is ends up being negative AP over square root of 6 divided by P, or they're also saying that this is going to be in the negative direction, right? So they're saying it's going to be negative right there. It's already the moment is already negative. So we're just finding the distance right in there. So all they're saying is a over the square root of 6. Was that worth it? I don't know. Was it worth it? Did you watch the video all the way through? Why? I don't know. Is it useful? The other example is better than this. And it's like 20 minutes of our lives we're not getting back. I could have been home. There. Something satisfying about getting a video for each of the topics we asked. Maybe. Who knows?